Properties of light and visual function. Light may be defined as the energy to which the human eye is sensitive. Scientists do not yet fully understand the true nature of light in the physical sense, but the behavior and properties of light have been extensively studied and are well known. The electromagnetic spectrum and optical radiations. The optical radiations lie between the X-rays and microwaves. This whole is the electromagnetic spectrum. It starts from gamma rays, then X-rays, then ultraviolet, then visible, then infrared, microwaves, and radio waves. Gamma rays is the most energetic because it has the least wavelength, while on the other hand radio waves is the largest wavelength and the least energetic. The optic radiation lies between the X-rays and microwaves. The optic radiation consists of infrared, visible light, and ultraviolet light. The optical radiations is subdivided into 7 bands. Each of these 7 wavebands group together wavelengths which elicit similar biological reactions. These 7 domains are ultraviolet C, ultraviolet B, and ultraviolet A, then visible, then infrared A, infrared B, infrared C. The ultraviolet C ranges from 200 to 280 nanometer. The ultraviolet B from 280 to 315. The ultraviolet A from 315 to 400 nanometer. Then visible radiation from 400 to 780 nanometer. Then the infrared A from 780 to 1400. Infrared B from 1400 to 3000 nanometer. And infrared C from 3000 to 10,000 nanometer. As with all electromagnetic radiation, the shorter the wavelength, the greater the energy of the individual quanta or photon or optical radiation. So ultraviolet C will have the shorter wavelength and the greatest energy. Ultraviolet BC and infrared BC. These are absorbed by the cornea and sclera. So the cornea and sclera absorb the optical radiation of the very short wavelengths, the ultraviolet BC, and the very long wavelength of the infrared B and C. The ultraviolet A is strongly absorbed by crystalline lens, while the wavelength in the range of 400 to 1400, from 400 to 1400, which consists of visible light and infrared light, near infrared light. They pass through the ocular media to fall on the retina. The visible wavelength then simulate the retinal photoreceptors, giving the sensation of light, while the near infrared may give rise to thermal effects. Because the refractive surfaces of the eye focus the incident infrared radiation on the retina, it can cause retinal damage, for example, eclipse burns. Now the visible light and color vision. The visible wavelength of electromagnetic spectrum are between 400 and 780 nanometer. The color of any object is determined by the wavelength emitted or reflected from the surface. White light is a mixture of wavelengths of the visible spectrum. Color is perceived by 3 populations of cone photoreceptors in the retina. These, which are sensitive to light of short wavelength, is blue, middle wavelength green, and long wavelength red. Short, middle, and green. Color defects. Congenital color vision defect occurs if a cone pigment is absent or if there is a shift in its spectral sensitivity. Hence, deuteranopia, protanopia, and tritanopia indicate absence of green, red, and blue cone function, and deuteranomaly, protanomaly, and tritanomaly indicate a shift in the corresponding cone sensitivity. X chromosome carries genes encoding for red and green pigment. So the X chromosome carries gene encoding for red and green pigment, whereas chromosome 7 carries the blue pigment gene. Of men 8% and of women 0.5% have a defect of the red-green system. The commonest is deuteranomaly. Deuteranomaly, which occurs in 5% of men and 0.3% of women. Tritane defects are rare. Congenital color defects characteristically affect particular parts of the color spectrum. Acquired color defects occur throughout the spectrum but may be more pronounced in some regions. For example, acquired optic nerve disease tend to cause red-green defects. An exception occurs in glaucoma and in autosomal dominant optic neuropathy, which initially cause predominantly blue-yellow deficit. It has recently been found that visual field loss in glaucoma is detected earlier. A perimetry is performed using a blue light stimulus on a yellow background. Acquired retinal disease tends to cause blue-yellow defects. Acquired retinal disease, except in cone dystrophy and in Stargardt, which cause predominantly red-green defects. So red-green in cone dystrophy, Stargardt, and optic nerve disease, while in glaucoma, blue-yellow. Testing color vision. Clinical tests of color vision are designed to be performed in illumination equivalent to afternoon daylight in the northern hemisphere. The first test is Farnsworth. This is spelling is wrong. It is Farnsworth, F-A-R-N, Farnsworth Munsell FM 100 FMHU 100 test. It is the most comprehensive method. It comprises of 84 color discs numbered in sequence on the undersurface and divided into 4 groups of 21. The colors of each group occupy a portion of the color spectrum. The colors differ only in the hue and have equivalent brightness and saturation. Each group must be arranged in a row with the reference colors at each end and the intervening disk in order of closest color match. The order of placement indicates the nature of the color defect. The D15 test uses colors from all parts of the spectrum which must be arranged in order from a single reference color. The test does not distinguish mild color defects, but for most purposes, those passing the test are unlikely to have problems with hue discrimination. Ishihara test. So Ishihara pseudo-isochromatic test plates specifically test for congenital red-green defects. Congenital red-green defects, the most common abnormality of color vision. The test plates consist of random spots of varying isochromatic density. Numbers are wavy lines for illiterates, and numbers for illiterates are represented by spots of different colors. A patient who is colorblind will see only a random pattern of spots or incorrect numbers. The figures can only be distinguished from their background by their color and not by a difference in contrast. Next topic is the ultraviolet light. The retinal photoreceptors are also sensitive to wavelength between 400 and 350 nanometer. 400 and 350 nanometer. In the near ultraviolet, this is near ultraviolet. These wavelengths are normally absorbed by the lens of the eye. In aphakic eyes or pseudophakic eyes with intraocular implants without ultraviolet filters, such ultraviolet radiation gives rise to the sensation of blue or violet colors. Newly aphakic patients frequently remark that everything looks bluer than before the operation. Of greater concern is the recent evidence that wavebands between 350 and 441 here nanometer in the visible spectrum are potentially the most dangerous for causing retinal damage under normal environmental conditions. It is therefore desirable that intraocular lenses filter out these wavelengths and protect the retina. Intraocular implant lenses are therefore being produced which incorporate ultraviolet A absorbing substance. The bright illumination employed in modern ophthalmic instruments may also cause retinal damage under some circumstances. Prolonged exposure to high-intensity indirect ophthalmoscope illumination, intraocular light pipe illumination, operating microscope light is potentially damaging to the retina, which may, in many instances, already be unhealthy. Some instruments have yellow filter built into them to reduce exposure to the most damaging wavelengths. Fluorescence. Fluorescence is the property of a molecule to spontaneously emit light of a longer wavelength when stimulated by light of a shorter wavelength. For example, the orange dye fluorescein sodium when excited by a blue light. This is blue light, whose wavelength is 465 to 490 nanometer. It will emit yellow-green light between 520 and 530 nanometer. Fluorescence angiography allows the state of retinal and choroidal circulation to be studied by photographing the passage of fluorescence through the vasculature after it has been administered systemically. White light from the flash unit. So this is camera flash. So white light from the flash unit of a fluorescent camera passes through a blue excitation filter. To eliminate the fundus with blue light. The wavelength transmitted by the excitation filter approximate to the absorption spectrum of fluorescence. Most of the light is absorbed, some is reflected unchanged, and some is changed to yellow-green light by fluorescence. The blue reflected light and a yellow-green fluorescent light leaving the eye are separated by a yellow-green barrier filter into the camera. This blocks blue light and exposes the camera only to yellow-green light from the fluorescence, thereby delineating vascular structure and leakage of the dye. The phenomena of pseudofluorescence occurs if there is an overlap in the spectral transmission of the excitation and barrier filters. This allows reflected wavelength at the green end of the blue to pass through the barrier filter and appear as fluorescence. Other important applications include the staining of ocular surface defects. Here you can see dendritic ulcer, viral keratitis, anterior segment angiography, the measurement of aqueous humor production and outflow, and in light microscopy, the localization of tissue constituents using fluorescein bound to specific immunoglobulins. Endocyanine green dye is a fluorescent substance which absorbs 805 nanometer and emit 835 nanometer in the infrared radiation. The retinal pigment epithelium does not absorb these wavelengths, and it is therefore possible to observe fluorescence of the choroidal circulation after ICG administration intravenously. Only 4% of 805 nanometer radiation absorbed by the ICG is emitted at 835 nanometer compared with total fluorescence of fluorescein. ICG angiography is not yet in general clinical use, but it has been shown to delineate occult choroidal neovascularization not visible with fluorescein. ICG has also been used to photosensitize vascular lesions to diode laser photocoagulation. Wave theory applied. The path applied through an optical medium, for example glass, is always straight if no obstacle or interference between the optical media is encountered. Diagrammatically, light is represented as a straight arrow line, or ray. By tradition, optical diagrams show rays traveling from left to right on the page. However, some experimental observations of the behavior of light are not fully explained by the simple concept of light as rays, and it is now understood that light really travels as waves, although its path is often represented by a ray. This figure illustrates the different ways of depicting the progress of light away from a point source. The A shows the light as rays, the B shows the wave motion of each ray, the C show illustrates the wave front set up by the combined effect of many rays, the concentric circle being drawn through the crest of the waves. The same effect is seen if a stone is dropped into still water. Viewed from above, circular waves travel outward from the point of impact. If the process were viewed in cross-section, the waves would appear as the ripples traveling away from the center of disturbance, as shown in this B picture. Wave motion consists of disturbance or energy passing through a medium. The medium itself does not move, but its constituent particles vibrate at right angle to the direction of travel of the wave. Imagine a ribbon tied to a rope along which a wave is thrown. The crest of the wave moves along the length of the rope, but the ribbon moves up and down at one point on the rope. The wavelength is defined as the distance between two symmetrical parts of wave motion. One complete oscillation is called a cycle. For example, XY between X and Y is one cycle, and it occupies one wavelength between X and Y. The amplitude is the maximum displacement of an imaginary particle on the wave from the baseline. A is the amplitude. Any portion of a cycle is called phase. Any portion of a cycle is called phase. So, if two waves of equal wavelength but not necessarily of equal amplitude are traveling in the same direction but are out of step with each other, the fraction of a cycle or wavelength by which one leads the other is known as the phase difference, as you can see in this picture. This figure shows two waves of equal wavelength which are out of phase by 1/4 of a wavelength. 1/4 of a wavelength. So phase difference equal to 90 degree. The complete cycle is 360 degree. So there is phase difference of 90 degree. So light waves that are out of phase are called incoherent, while light waves exactly in phase are termed as coherent. Now interference. When two waves applied travel along the same path, the effect produced depends upon whether or not the waves are in phase with one another. The waves are in phase between one another. If they are in phase, the resultant wave will be a summation of the two. Here you can see. And this is called constructive interference. If the two waves of equal amplitude are out of phase by half a cycle, they will cancel each other. This is known as destructive interference. The final effect in each case is as if the waves were superimposed and added, in algebraic sense, to each other. Phase difference of less than half cycle thus result in a wave of intermediate amplitude and phase. Destructive interference is shown here. occurs within the stroma of the cornea. The collagen bundles of the stroma are so spaced that any light deviated by them is eliminated by destructive interference. Interference phenomena are also utilized in optical instruments. One example is low reflective coating, which are applied to lens surface. The coating consists of a thin layer of transparent material of appropriate thickness. Light reflected from the superficial surface of the layer and light reflected from the deep surface of the layer eliminate each other by destructive interference. Diffraction: when a wave front encounter a narrow opening or the edge of an obstruction, the wave motion spreads out on the far side of the obstruction. It is as if the edge of the obstruction acts as a new center from which the secondary wave fronts are produced, which are out of phase with the primary waves. This phenomenon is known as diffraction. The intensity of the light falling on the zone AB, here you can see, is reduced to some extent by interference between the primary and secondary waves. The light falling on zone BC is derived from secondary waves alone and is of much lower intensity. When the light passes through a circular aperture, a circular diffraction pattern is produced. This consists of a bright central disk surrounded by alternate dark and light rings. The central bright zone is known as airy disk. Diffraction effects are most marked with small apertures and occur in all optical systems, including lenses, optical instruments, and the eye. In the case of lenses and instruments, the diffraction effect at the aperture used is negligible compared with the other errors or aberrations of the system. In the case of eye, diffraction is the main source of image imperfection when the pupil is small. However, the advantage of a large pupil in reducing diffraction is outweighed by the increased effect of the aberration of the refractive element of the eye. The principle of diffraction is used in the design of some multifocal intraocular lenses.